we have a break. So we'll have 2 talks, and in between the 2 talks, we'll have a break, the famous virtual coffee break. And the idea is that, will you do that, Hula, too, this time? Yes, you know how to do that? Okay, great. So Hula will send us in a virtual coffee room. There will be about 10 people in each room. You are free to join the room or not, but we will be there. You can chat here with and talk for 10 minutes with some colleagues, randomly selected colleagues. And after the 10 minutes, we will all go back to the main room. And of course, if you take a real coffee, you can also just leave the session for 10 minutes and come back when you want. Ole, do we still have some people coming in?
I think it's okay to slowly start and set up the slides.
Okay, so Roman, Romance, you spell the S, I guess? Okay, I can't see this. I have a problem with my computer. I think I can't see the slide. I see, here they are. Here they are. Okay. So yes, I think we are ready now. So as we said, this is the first, as you may know, this is the first of a series of 2 seminars that are dedicated to the social choice and welfare meeting that was supposed to be held in Mexico next week. As you know, well, we are all stuck in our home countries. So I'm virtually in Mexico today. And so we'll have at each day for this week and next week, we'll have one of the plenary speaker of the session. And we'll have also one of the local organizers who will present its work. So if you have questions during the talk, please use the chat, put the question. Usually what we do is that the speaker will do his speaks and we will review the chat afterwards to see what are the questions. Of course, the co-authors can also try to answer the chat during the talk if they want to give some clarification and stuff like that. So today we first, of course, the seminar is recorded. So if you miss some part, the records will be put on the website sometime after the seminar. So today we have a seminar. The first seminar will be presented by Roman Spax from Instituto Tecnológico Autónoma de México. And this is about electoral maldistricting. So Romance, you have about 20 minutes to present your work. Enjoy the talk.
Thank you very much, everybody. So this is joint work with Andrei Gomberg and Tridip Sharma, all of us at ETAM. So let me present the question, then I'll tell you what we do about it. Here is a US state, the state of Georgia. The unit of observation on this map is an electoral precinct, and the color denotes how Republican it is. So if the color is very red, it means it's very Republican. If it's very blue, it means it's very Democratic. And we measure Republican versus Democratic by voting behavior in the 2008 presidential election, whether somebody voted for McCain or for Obama. So every state has the state legislature. In Georgia, this is the House of Representatives, the lower chamber of the state legislature. And the problem is to elect members of the state legislature. So here I have 5 of them in this picture. How is it done in practice? In practice, electoral precincts are partitioned into electoral districts. So in this picture, there are 5 electoral districts and 1 representative is elected from every district. Okay. So what is the question that we ask in this context? The question is the following. So in the context of existing literature, some papers in the literature ask the following question. So how do you how do you partition a state into electoral districts in order to meet a certain partisan objective? For example, to influence the policy. Other papers ask, how do you district in order to maximize the welfare of voters? What we do, in a sense, we invert these questions and we say, given the district map that we observe in the data, how can we infer the intention of the districtor? What was the objective of the districtor? What was maximized? And one way to summarize our answer is in terms of an index of maldistricting. So the way we compute the index of maldistricting is as follows. We have a legislature that we observe in the data. I'll explain to you in the context of the model what a legislature looks like. And then we compute two sets of legislatures, well-districted legislatures, which will maximize the welfare of voters, and then maldistricted legislatures, which serve some partisan objective function. And we compute the distance from the observed legislature to the closest well-districted legislature to the closest maldistricted legislature, and the index of maldistricting is a monotone function of the ratio of these distances. So in particular, if the observed legislature is very close to the set of maldistricted legislatures so that dm is small, then the value of maldistricting index will be close to 1, okay, indicating a lot of maldistricting. A large part in our project is just characterizing the set of implementable legislature. That's the legislatures. This is the first thing we have to do. Then we can compute, maximize over that set to find welfare maximizing legislatures and then maldistricted legislatures. And then we can compute our index. So one comment on how we interpret the exercise that we do. Okay? So there are two kinds of questions you can ask about districting. So one kind of questions would be how bad for the voters the districting is, and another one, what was the intent of the districtor. So in law, it's important whether there was intent to do damage, whether damage was done, but also whether there was intent to do damage. Now, if somebody falls from the balcony and I push him, if it's important to know, in order to detect my guilt, it's important to know whether it was intentional, or it was unintentional. So if maldistricting, electoral maldistricting were illegal, then it would be important to know the intent of the districtors. According to the current law, it's not illegal to gerrymander or to maldistrict for now. Okay? But the question we ask is really about the intent, not whether the districtor kind of hurts the voters, whether the current map is bad for voters, but rather what was the likely intention of the districtor. Okay? So let me jump into the model. It's one slide. We have a square of voters who are uniformly distributed on a square here. The horizontal axis is interpreted as a set of locations, and then you have uniformly distributed mass of voters living at every location. Every voter is either of ideology 0 or ideology 1. You can interpret ideology 0 as a Democrat, ideology 1 as a Republican. The economy is completely characterized by an affiliation function, which is a weekly increasing function, and it shows at every location what's the proportion of Democrats and what's the proportion of Republicans. So at this location, there are a lot of Republicans, few Democrats. At this location, few Republicans, a lot of Democrats. So without loss of generality, we relabel locations so that this function is an increasing function, rho. How do we construct a district map out of it? We just partition the set of locations into a desired number of districts. So for example, if there are 3 districts, here is how we can construct 3 districts. Here is a pink district consisting of 2 intervals. Then there is a green district consisting of 2 intervals, the blue district consisting of 1 interval. All districts have to be of the equal size. This is the constraint that the districtor faces in practice. Yeah? And a district map induces a legislature. Okay, how does that work? We'll look at the average ideology, average of the 0s and 1s in every district, and we plot it on the vertical axis. And this we assume is the ideology of the representative who is elected from the district. So in the blue district, it's more to the right, so the voters are more Republican, so the ideology of the elected legislator is higher. This assumption can be motivated by the mean function theorem. Not the median function theorem, but the mean function theorem. So then a legislature is a collection of real numbers, we normalize this collection, the legislature, so that these numbers are non-decreasing in the vector. And then we assume that the legislature kind of comes together and they vote on a policy, and the policy that they eventually adopt corresponds to the median ideology of the legislators. Okay? So here with 3 districts, the median is R2. Okay, so this is the model. You may point out that the world is 2-dimensional, the model is 1-dimensional. The way we deal with it, we just look at all the locations on the 2-dimensional map, electoral precincts, we rank them according to their ideology, put them on a line, and this way we collapse a 2-dimensional map into a 1-dimensional map. So we shall work with a 1-dimensional map. Okay, so the first thing we have to do is to characterize the set of all implementable legislatures. Okay, a legislature is a vector of k dimensions. A legislature is implementable if it can be induced by some district map, which partitions the interval of locations into k electoral districts, each of which has the same size. Okay? So our first result is a characterization of all implementable legislatures. First, I'll just illustrate it in an example with 3 districts, and I'll use this picture later on in the talk as well. So if there are 3 districts, I can depict the set of implementable legislatures in 2 dimensions, just as I would depict a probability set of lotteries in a probability simplex. So there are 3 legislators. On the horizontal axis, I have the ideology of the first one. On the vertical, I have ideology of the second one. The third one points at you, so it's projected away. You cannot see it, but there's a linear relationship between all of those ideologies of legislators. They add up to the same number, so you can infer the third dimension. I've projected it away. There is a question? No, there was some noise. Okay. So I have normalized the legislature so that R2 is greater than R1. So the set of implementable legislatures is above the 45-degree line. So every point inside of this polytope is an implementable legislature. And you can read off kind of the maximal implementable policy, for example, from this point, the minimal implementable policy, which is the median R2 from this point. Another special point in this picture, which I'll come to in the next slide, is this point, this vertex. This is an extreme legislature. It's important because it characterizes the entire feasible set of implementable legislatures, as I explain in the next picture. Okay, so in the next slide I meant. So here is the next slide. This is a proposition which characterizes the set of all implementable legislatures. So the following statements are equivalent. A vector R is an implementable legislature. A vector R is less informative about voter ideology than the extreme legislature. So the extreme legislature is this point in the example with 3 districts. I'll explain on the next slide what I mean by less informative. Then there are 2 kind of purely technical ways to characterize the set of implementable legislatures. One is through majorization. Again, the extreme legislature is prominent here. Any implementable legislature is majorized by the extreme legislature. Majorized is a series of inequalities. I will not explain it separately. Another way to characterize the set of implementable legislatures is by characterizing the vertices of the implementable polytope. So if you have k districts, in the previous picture we had 3 districts. So 3 minus 1 is 2, 2 to the power of 2 is 4, so we should have had 4 vertices in the previous picture, which we do. And there is a simple expression, explicit expression for each of those vertices. So we can characterize it for an arbitrary k, and that's another way to characterize the set of implementable legislatures. Okay. So let me comment briefly on the equivalence between 1 and 2. So equivalence between 1 and 2 says that the legislature is implementable if and only if it is less informative about voter ideology than the extreme legislature. So the extreme legislature I've already introduced. Another way kind of to see it, how you generalize it, is the following. To construct an extreme legislature, I construct a district map such that ideologically adjacent voters are put together. So I pick a number of voters who are most to the left ideologically, and I put them together into District 1, and then most to the right, and I put them together into District 3. And then in the middle, I put them into District 2. And this generalizes for any number of districts. So that's the extreme legislature. And the claim is that the legislature is implementable if it's less informative about voter ideology than the extreme legislature. So any legislature can be viewed as a signal about voter ideology, or any district map can be viewed equivalently as a signal about voter ideology. Suppose the only thing I told you about the voter is the district in which he resides. Then you can look at the mean ideology in the district and you make some inferences about what's the likely ideology of this randomly selected voter in the district. So in that sense, a district map, a legislature is a signal. And then a legislature is implementable if it's a less precise signal about a voter ideology than the extreme legislature. And this notion of less precise can be made exact, and this is in the traditional Blackwell sense, okay? Less precise, okay? From this proposition, you can also do some comparative statics. Kind of why it's important, just to signal that the model is tractable. There are a lot of things you can do with it. We've chosen for the purpose of the kind of presentation to construct this index of maldistricting, but you can do many other things with the model. So here is an interesting comparative statics that you can do. The proposition says that more legislatures are implementable when a location is a more informative signal about voter ideology. So I'll unpack this statement, okay, with pictures again. Okay, so this polytope of implementable legislatures, which we have already seen, actually is drawn for the state of Georgia. And here is another polytope, which is pink. And this is drawn for the state of Arizona. Okay? And it happens that the polytope of implementable legislatures for Arizona is smaller than for Georgia in the inclusion sense. And if you look at the underlying row functions, which characterize the ideology at a location, the row function for Georgia second order stochastically dominates the row function for Arizona. So if you viewed these row functions as CDFs, which they are not, but if you pretend these were CDFs, then you can mechanically apply the second order stochastic dominance order to them. Okay. And the claim is that geography in Georgia is more informative about the ideology of voters than in Arizona. I mean, why, if you pick, say, this location, then you're pretty sure that the random voter you pick in Arizona at that location, sorry, the random voter you pick in Georgia at this location is a Democratic voter. In Arizona, you're less sure. Okay. The same here, if you pick a rather allocation to the right, and in Georgia, you're pretty sure that the voter there will be Republican. In Arizona, you're less sure. So the closer this row function is to a step function, the more informative one's location is about one's ideology. And intuitively, kind of, if location is more informative about ideology, then you can put together locations in a way to achieve more things. And this is what this proposition makes formal. In the inclusion sense, you can achieve more things. Okay, so I've characterized the set of implementable legislatures. Now I'll tell you how we define the set of maldistricted legislatures, well-districted legislatures. Yeah? So we assume that the set of maldistricted legislatures is the set of legislatures which either maximize the policy or minimize the policy. So a Republican would want to maximize the policy, the Democrat would like to minimize the policy. We can explicitly compute these maximal policies, minimal policies. We can explicitly compute the underlying district maps and underlying legislatures. Yeah? So the case of well-districted legislatures. Here is the definition of a well-districted legislature. So we say that a legislature is well-districted if it maximizes a social welfare function from a class. The class is parameterized by gamma. Gamma is a weight, a relative weight on two components. One component is the disutility from policy. So the assumption is that every voter has an ideal point, which is 0 or 1, and fraction rho L of voters at location L have an ideal point 1, and then these voters will experience disutility 1 minus p squared from the policy that the legislature adopts. And then the complementary fraction have the ideal point 0, so they experience disutility p squared. And the second component is the disutility from the ideology of the representative in your particular district. So for agents, voters at location L, this R of G of L is the ideology of the representative elected from the district of which location L is a member. And the assumption is that individuals like to be close ideologically to the legislators who represent them. Okay? And we're agnostic about which of these two terms is more important. We look at the entire class, and if the legislature is in this class, maximizes this function, then it's a well-districted legislature. Okay? And the final step in the construction of our index is the definition of a distance between two legislatures. Okay? So here is the story that motivates our choice of the distance being L1 norm, or the Manhattan distance, or the taxi cab metric. Okay? So here is the idea. We observe some legislature in the data which will not necessarily be maldistricted or well-districted. It will be the intended legislature which could be maldistricted or well-districted plus some noise. Okay? So the districtor draws a map intending either well-districted or maldistricted legislature. What he doesn't anticipate is that voters move randomly. And because they move randomly, after they have voted, the observed legislature will depart from the intention of the legislator. Okay? So then we define the distance between two legislatures as the smallest measure of voters who must move so that you transform one legislature into another legislature and given a district map. Okay? And in the definition of the distance, we're minimizing over the district maps that induce both legislatures. So then it turns out that the appropriate distance is a Manhattan distance. Okay? So you can view this just as a definition of the distance that we employ, and the rest is just a story, a motivating story. I mean, why we view Manhattan distance, say, more appropriate than Euclidean distance. Okay, and now we're ready to construct our index of maldistricting. So in the example of Georgia, but with 3 districts, suppose this white point is the observed legislature, then the maldistricted legislatures are the maximal one here and the minimal one here. And the set of well-districted legislatures is this hockey stick. We can characterize this set in general. I just give you an example in this picture what it looks like in this particular case. And then we can compute the distance to the closest maldistricted legislature, which will be the legislature that maximizes the policy, and the distance to the closest well-districted legislature, which will be this distance. The distance is not a straight line because this is a Manhattan distance. And then we plug in these distances into our index, and we get an index of maldistricting. Okay? So let me conclude with saying what happens if you use the data for 40 US states. Okay, so we do this exercise for 40 states. What's a location in the model is a precinct in the data. What's ideology in the model, the row of L, the fraction of Republicans at a location, is the fraction of votes that were cast for McCain in the 2008 presidential election. A legislature is the lower chamber of the legislature of the state legislature for every state. Okay? And here is the result for some 40 or so states, from least maldistricted legislature to most maldistricted legislature. Okay, so this picture kind of proves that our model is tractable enough so that we can take it to the data And you can view as a holy grail the computation of indexes of maldistricting, or alternatively, you can say that the journey is the reward, and we have identified a model of districting which is very tractable. We can explicitly characterize the entire set of implementable legislatures, and there are a lot of things we can do with it. We can maximize over it. So I maximized over it to find well-districted legislatures, maldistricted legislatures. You can enrich the model, it will still be tractable. So you can view the contribution as being methodological. You can also view the contribution as being kind of getting an index of maldistricting that reflects the intent of the districtor. So I'm done and I'm ready to take questions.
You're muted, Vincent.
Yeah, you can unmute your microphones and we can thank the speaker. So we had a few questions in the chat.
I can see that Andrei Gomberg has been very active on the chat, so maybe some of those questions have already been answered.
Of course, the big question is about the contiguity, of course, of the districts, because you're plotting we have two questions, one by Bill Zwicker, by one Omerlev, and we already have some answers. So of course, the big question is you don't take into account the geographic constraint about the contiguity of the district.
Mm-hmm. So we have a theoretical justification for this. The theoretical justification would be that theoretically it doesn't matter. So there is a paper by Scherstug from 1998, which has proposition number 4, which says that take any district map, you can approximate this district map with a contiguous, geographically contiguous district map. So it's not ex ante obvious, but you can draw very thin shoestrings from the disconnected components of a district to make it connected. So in theory, it's not an issue. In practice, this is something that could matter, and we neglect this. So we assume that it's very easy to do in practice whatever the districtor can easily do in theory, and by shoestrings connect disconnected components. And if you look at the shapes of electoral districts, some of them indeed look very strange in practice.
Two questions in the chat. William, just go ahead. Just go speak. Speak to us, William. No, you do not want.
So I had a question about your table comparing charts for the index of for your index. How would that compare to lining up the states by how ideologically homogeneous they are? States that are fairly balanced with Democrats and Republicans versus states that are almost all Democrat or almost all Republican.
Okay, I'm trying to recall what we've done. One thing we've done, we've plotted we've done this. We've plotted mean ideology in the state against our index. So one thing you might expect is some, say, U-shaped relationship or hump-shaped relationship in which, as things depend on how far you are from one half. So it turns out that there is no relationship. There is no relationship between our index and how ideologically homogeneous a state is.
Okay. Matthias, can you give your question?
Hi.
Yes.
Yes. Okay. So, I mean, I was particularly focusing on your chart showing index of the different states, right? So are you aware of this contribution by Chris Chambers and Alan Miller on the index of bizarreness and how bizarre are the districts of electoral districts?
Yes. So we haven't plotted their index against our index. That's one. Two, we completely ignore geographies. So there is no bizarreness, but we just have no language in our model to speak about the shapes of the districts on the map, because at the very beginning, the first thing we did,
in the building of the index?
In our index, bizarreness, how bizarre it looks on the map, it's completely ignored because we have ignored the constraint of contiguity on the map.
Okay.
So as I showed in one of the early slides, we take the state and then we rank all the precincts in the ascending order of their ideology, and we line them up, and we forget about what it looks like on the two-dimensional map. So our measure is complementary, doesn't directly speak to the bizarreness of the shapes on the map.
Okay, thank you.
If I'm right, I don't follow American politics every day, but if I remember well, there was some debates last year at the Supreme Court about about the gerrymandering issues, and there was a lot of debates about measuring gerrymandering. So I guess your paper is in the line of all the papers that in the last years I've tried to say this state is more gerrymandered than this other one, etc., etc., etc. Am I right?
Yes, we contribute to that literature.
But I guess at the moment the case are closed at the Supreme Court. Basically, the Supreme Court dismissed everything, if I'm right, no? Do you have any news about that? Maybe
that's right,
Bill?
but given how long it takes to write a paper in economics, maybe in 5-10 years, our paper will again become topical. And it's about to be out.
Yeah, of course. Even if the Supreme Court says it's not an issue, it may come back. It may be an issue. It's not an issue. Are there any other questions? There are some comments in the chat, but there might even be exchange between colleagues about the blocks and the precincts. I think, do we have any other question? No? Okay, so we'll thank again the speaker.
Thank you.
And Ule will send us to the famous virtual coffee break rooms.
Give me a moment. Yeah, you can first make an announcement or ask another question.
We'll sometimes make change or difference from seminar to seminar. So this time we were 1 hour later. So if you have comments about this change, if it's good or bad, just send us emails to me, to Ule, and we'll see if it's better. Our usual time is 3 p.m. in Europe. We have most of our speakers are from North America and Europe, we noticed. But if you think it's better to be at 4 p.m., if it's better, not better. But of course, if we go later, then people in the Middle East or Asia are not very happy, so who knows that. But still, if you have comments about the format of the seminar, please do not hesitate to send us an email. See you.
All right, I'm going to start calling people back, so we'll start in around 1 minute. Vincent, you are muted, and I believe we are complete.
Yeah, I think that's what I was saying. I think that we are now back again. Everybody's back again, more or less. So we will start we'll go to our second speaker with Jordi Massó. So Jordi was supposed to be a plenary speaker in Mexico next week, but we'll have a chance to have him today. So I think everybody knows Jordi. He's a very famous social choice scientist and game theorist at University Autònoma de Barcelona. Okay, someone suppose we have breakout rooms before the meeting too. Okay, maybe that's an improvement. Jordi will today present his paper. All sequential allotment rules are obviously strategy proof. So Jordi, the floor is yours.
Thank you very much, Vincent. Can you hear me well? And I guess you see also the screen, yes? So this is a joint paper with Pablo Rivillaga and Alejandro Nene. They are both at the Universidad Nacional de San Luis and the CONICET in Argentina. The goal of the paper is to show that in the division problem with single peak preferences, all sequential allotment rules are obviously strategy proof. What the remaining of the time, I will explain what is a division problem, what are the sequential allotment rules, and what is obviously strategy proofness. And I guess that from that you will understand the interest of such a result, which in this literature is a bit surprising because this is a large class of rules. Just to describe the division problem, it's a very simple problem. We have a fixed set of agents. There are a number of units, indivisible units, more than 2, of an identical good, that they have to be allotted among the set of agents. Exactly the k units, no more nor less. So we have these units, and everybody should have some share of this number of units. And a set of feasible allotments then is for every agent, a particular number of integer number between 0 and k in such a way that we are exactly allotting the k number of the k units. This is an instance and has been studied a lot because it's an instance of a private goods case. The alternatives, to describe a social alternative, we have to describe the private components. But for the reason it makes sense in many settings that we assume, it makes sense to suppose that an agent will be indifferent between 2 different allotments as long as he has the same assignment. Yes, and this is why we will consider strong domain restrictions, and that's why you cannot apply directly impossibility results. Yes, so we assume that the agent will have preference on the number of units that he will receive. Yes, and the assumption I will justify in a bit is that these preferences are single peak. So every agent has the top. This is the best, unique best amount. And so it's strictly better than anything else. And as we move away from the top, as he consider allotments that are strictly less than x or strictly larger than x in the 2 sides of the peak, the alternatives are getting worse and worse. Yes? So this is the single peakness assumption where tau is the top. These are going to be the set of single peak preferences on the set of integers from 0 to k. Now, given a division problem, now is characterized by the set of agents and this number of units. And now, given a profile of tops, the ideal points at the top of everybody, now the optimal the optimal allotment will not be in general compatible. And there will be either more or less. The sum of the optimal allotments will be larger or smaller than k. And this is arises how we should allocate if the tops are not exactly, the sum of the tops are not exactly equal to k. Yes, we would like to take into account the preferences in order to allocate the k units given a particular top. This is probably some of you have already realized, this is the discrete version of Sprumont in 91. And examples of that is the allocation of hours of work when the wage is fixed and agents have strictly quasi-concave preferences. So if you look at the budget set, it induces on the space of leisure and money preferences induces a single peak preference on the budget set. It's the same if we have a number of shares of a risky asset. different attitudes toward risk and incomes may determine different levels of optimal consumption. There is a large literature on social choice that studies such type of problems. Yes, so rule is exactly a systematic way of solving the problem. Yes, we want to take the choice of the allotment by taking into account the preference of the agents. And the first natural requirement is that the strategy proveness of the rule. That is that truth-telling is a weakly dominant strategy in the direct revelation mechanism. I want to emphasize here that there is not an issue here of constructing mechanisms. We know it, that without loss of rationality, we can focus on the direct revelation mechanism where strategies are preferences and we have the outcome function to be the same social choice function, the same rule, correct? Now, so this is the first requirement in using truth-telling as a dominant, quickly dominant strategy. The second and also natural requirement would be efficiency. And the efficiency requirement is that for every profile, the rule chooses a Pareto optimal allocation. There is no way of improving somebody without making worse off somebody else. Yes, so this is efficiency. And also, it's easy to see that under single pigness, efficiency together with single pigness is equivalent to require that the agents will have to receive below the tops, everybody, when there is a scarcity. So when there is more, people want more than there is available. And below the tops, whenever is excess. Yes, so with single pigness, efficiency is equivalent to this same-sidedness property that says if everybody wants more than what is available, okay, now everybody should receive less or equal than the top. And if the sum is less or equal than what is available, now everybody should receive more. So the rationing is everybody's in the same side of a ration, and this is a consequence of efficiency. The third property I wanted to say is and we are going to use, is the replacement monotonicity property. And the property is just restricts the way that the rule will change when an agent changes. So take a profile and an agent, and now suppose the agent says something else, and suppose that he's getting more than he was getting. Yes, the requirement will say that then, since there is a fixed number of units, if he's getting more, now what this property says that everybody should go in the same direction. That is, that after the change of the preference of the agent I, now everybody should get less or equal than before. So since this has to happen, so if this is equal, whenever this is equal, when the agent doesn't produce a change, changing his preferences, then this means that this will have to be equal. And this is exactly the property of non-bossiness. The last property, in particular, when we're looking at situation with fixed pricing, where agents have endowments, they go with some amount, and the total K is precisely just the sum of the individual endowments, then individual rationality makes a lot of sense. Individual rationality, now we would say that everybody should receive an allotment that is at least as good as the amount that is guaranteed by the rule, by the individual rationality property. So this individually rational property will respect a particular allotment if everybody gets at least in terms of preferences as well as what he was getting at the original queue. Yes, and Topsonly, with the simplicity of the rule, all these properties would imply Topsonliness. So now it says that the rule only depends on the top, and hence we can talk, instead of phi of the profile, we can talk about phi of the vector of tops. Yes. So it's there is this paper in Games and Economic Behavior by Salvador Barbarama, Jackson, and Alejandro Neme that characterize the family of all strategy-proof, efficient, and replacement monotonic rules. Yes, the characterization identifies a class called sequential allotment rules that they describe, and this corresponds exactly to the rules that are strategy-proof, efficient, and replacement monotonic. If we add as a further requirement that the rule respects the individual rationality with respect to this allotment, then we get a subclass of sequential allotment rules are those that have the property that whenever everybody asks for 0, or whenever everybody asks for k, that the rule gives precisely the q. Yes. So among the set of sequential element rules, there is a subclass that they are individually rational with respect to particular k, and they have the property precisely that is the allotment if everybody has the extreme potential allotments. Yes. In the paper, we study the obvious. We ask the question whether all these sequential rules are obviously strategy proof. But now for the talk, I will restrict myself to individual rational rules. Yes. So first, I would like to give you a definition of the sequential element rules. To define a sequential element rule is going to be done in a sequential process. And since our rule will be individually rational, we start with this reference vector. No? So the idea is we are going to see reference vectors, reference allotments to the agents. Yes. So take a profile of tops. So I'm going to describe a rule. To describe a rule, I have to have the individually rational rule. I have to have this allotment Q. And now to describe the rule, I'm going to do it in several steps. So first, take a particular preference profile of tops. Yes, so those are the tops of everybody. And the question is, what is the rule? A sequential rule with a lot to this vector of tops. Of course, if this vector adds up to k, now the rule has to select this vector. Yes. Now the question is, suppose that the tops are larger than k, and the symmetric case will be for the smaller case. So now suppose that people ask for more. Now there are two cases that we have to distinguish. First, suppose that everybody is asking more than the reference allotment q. Yes. So suppose that this adds more than k. Remember that q is a feasible allotment. But now suppose everybody is asking for more. Now the rule has to give exactly the q. Yes. This is the way that is described in allotment rule. Otherwise, what happens if some agent is asking for less than the q? Of course, somebody has to ask for more because we are in the case that the sum is larger than k. So suppose that, let's look at the case where there are some agents that are asking for less than the reference individual rational allotment q. Now those guys are receiving the top. Yes. So we have to look at now who is asking for less, and those will receive the top and live with this amount. Yes, the remainder guys, now the reference vector q, the guaranteed endowment q, now will have to increase because there will be still amounts that they're not assigned to the individuals that left. And then a rule differs from each other on how now this amount left is distributed among the agents that stay because they have a top which is larger than the reference. And now once we have these new references, we ask again who has the top smaller than this new reference vector. Those guys receive the top and leave, and we keep doing that. Perhaps the best way is just to look at, I was thinking of giving an example, simple example for, I don't see, you hear me, no? Can you hear me? Yes, no, I guess, no?
Yes.
Okay,
yes,
good,
we can hear you.
Okay, good. And agents, the amount is 7 units, and the reference vector is 0, 1, 1, 5. That's the individual rational vector, yes? And now assume that the top is, the sum is larger than the q, yes? So this is 10, and we have to distribute it 7, yes? The question is how we are going to ration those guys, yes? So the rule works as follows. So observe that to give a rule, we have to first give this q. For another rule, the q of zeros and the q of k's will be another allotment, yes? So a rule is, in principle, is defined by this particular q. So now I'm plotting here the units, and here the different agents. And a circle is exactly the allotment q. In this case, agent 1, 0, 2 and 3, 1, and 5, and agent 4, 5. Yes, so I'm here describing the allotment for every agent, and this is also the top. Yes, the top of Mr. 1 is 5, 2 is 1, 3 is 2, and 4 is 2. Yes, so here I can describe the reference vector and also the tops. Yes, so how the rule proceeds? The rule proceeds by looking whose top, what is the set of agents whose top is below the reference. And in this case are agents 2 and 4. So the rule is going to give to those agents 2 and 2. Sorry, 1 and 2, which is precisely the top. Yes. Once we do that, now we have allotted 3 units. So now since we have 7, now it's like we have now 4 units to allot. That Mr. 2 and 4, they already got 1 and 2, so the 3 units. So there are still 4 units to be allocated. Mr. 1 had the reference 1, so 4 minus 1 is 3. We have to redistribute these 3 new left units among agent 1 and 3. And the way we do it, this is exactly what the rule says. The rule will tell us how to do it. So another way, if now I describe a way of allocating these leftover units, this will be final rule. But this way now, the only requirement has to improve. Everybody has to improve. Agent 1 should now, the net reference should be larger than 1. And for Mr. 3, agent 3 should be larger than 1. For instance, 1 and 3. Yes. And how this is done may depend on many things. What is the allotment that the agents that already left got, and so on and so forth. Yes, but now agent 3 is below the new reference, so he gets the top. So Mr. 3 gets the top, which is 2. And at the end, so there is 1 additional unit left, we give to Mr. 2, and that's it. He's the only one whose top is above, so he has to receive the reference allotment. And hence, this is the image of the rule at this profile, which is 2, 1, 2, 2. This describes a sequential procedure, and this is why it suggests naturally to ask for obvious strategy provenance. And I want to now to describe briefly what is the notion of obvious strategy provenance already referred to our setting. Lee proposes this notion as a way of dealing with agents that have limited contingent reasoning. Yes, making easy for the agents to identify that truth-telling is an optimal decision. So take a rule in our setting. There is the Lee definition is much more general, but in our setting we have a rule. A rule is obviously strategy proof if there exists an extensive for game, with the set of players being the set of agents, and with outcomes in the terminal nodes we have allotments with 2 properties. For every profile of preference, we should be able to identify a profile of behavioral strategies in the extensive form with a property that if the agents play this strategy, this is the outcome in the extensive form when agents play according to this strategy, this gives exactly the outcome that the rule selects at the profile R. And the second ingredient, is that for every agent and for every preference, this strategy should be obviously dominant. And what does it mean to be obviously dominant in an extensive form? So here we have an extensive form. I don't put the details. This is an extensive form, yes. And now let's consider this, let's call it truth-telling strategy, because after all, players will have to choose among subsets of preference, so we can identify when this is truth-telling. Take any other strategy that is different. So if it is different in the extensive form, it means that we should be able to identify the earliest point of departure between the 2 strategies. That is, nu is one of the first nodes in which the 2 strategies behave in a different way. Perhaps here player I has chosen something, but the 2 strategies were selecting the same. Remember, those are behavioral strategies. So we are a nu, and the 2 strategies propose different choices. So the notion is based on 2 very extreme behavioral assumptions, which is that when player I uses this strategy and makes these choices, he's absolutely pessimistic. He's thinking that among all potential outcomes that are possible, whenever he follows playing this strategy, but for all potential behavior of the others, Xi is the worst possible outcome. He thinks that the outcome of this action at the end will be the worst one, who is very pessimistic evaluating the truth-telling. And in the other hand, he's very pessimistic evaluating the alternative strategy. When he's here, he thinks that the best possible outcome will happen when he makes these choices. Yes, so the requirement of being obviously dominant is that precisely worst possible outcome associated to this truth-telling is at least as good as the best possible outcome, the optimistic point of view of the alternative strategy. So, this. So there are lots of quickly several literatures. Lee itself, yes. So this is the notion of obvious strategy proof. Lee itself shows that top trading cycles algorithm is not obviously strategy proof. Later, Rationality and Gorenzowski show that the deferred acceptance algorithm is not obviously strategy proof. I don't know how I'm doing on time, so I don't know how I'm doing on time. 5 minutes, okay. So
5 minutes max.
Okay, there are other positive results. If some of them are precisely looking at the case of a cyclic preferences identified proposed by Ergin to make the deferred acceptance algorithm obviously strategy proof, or Trojan that identifies a very strong necessary insufficient condition on the preference of the agents to make top trading cycles obviously strategy proof. There are other papers. Most of them are revelation principle-like results, because you have to realize that now the difficulty of the concept is that in general, we don't have the revelation principle. And so the question whether a rule, a social charge function, is obviously strategy proof turns out to depend on whether it exists or not as extensive for gain. And some of the results are trying to provide revelation principle-like results, saying for this type of problems, without loss of generality, we can look at this particular mechanism. For instance, one of those papers is Mackenzie, that it's a very, very nice paper in terms of this. But what is our result? Our result is that all sequential alignment rules are obviously strategy proof. Yes, so that there are ways of inducing truth-telling as a obviously dominant strategy if we'll find a particular extensive for gain. And the proof of this theorem is precisely constructive. So it's not just an existential type of result, it's not just a characterization, it's a constructive proof that what we do is for any given sequential alignment rule, we construct a particular extensive game form, gamma that depends on the rule, that implements the rule in obviously strategy proof, obviously dominant strategies. Yes, so this is the main contribution. Yes, and in this literature is a bit less rare because it's not just revelation principle. Is that we give exactly the rule for every game. So we have to construct, yes, what we call monotonic and individualized mechanism. We will, given the rule, we are going to construct the game in extensive form. We are going to construct the mechanisms that players will have to play in order to implement this rule in obviously dominant strategies. Yes? So again, we are now restricting to ourselves to the case that that the rule is individually rational. So we have that the rule maps proposes Q whenever everybody asks for 0 or everybody asks for K. And now the algorithm has two different stages. Yes, the first stage is just a stage in every step of the stage A. So now the stage is divided in different steps. Now the objective now is classify every agent according to whether the agent wants more, less, or exactly QI unit. So the QI will be used as a guaranteed reference in down allotment for the agent. Yes. So the agent will be able always to get this amount from the very beginning. Yes. So now we are asking the agents whether they would prefer this particular amount or they would prefer more or less. And so making them play one after another, in this case, the order is irrelevant. We can classify and obtain a partition of the set of players between among the set of players that would like to get more than the reference guaranteed allotment, or the players that would like to go down, that is receive less, or the agents that would say, I'm fine, the QI is fine for me, I like QI. Yes. So we do this partition. Yes, and now in the second step, in a second stage, now what will happen is that, okay, this is a reference vector allotment, but this will not be efficient in general. So now at stage B, what we will do is to identify every step, we will identify a pair of agents that perform a Pareto improvement from Q. And this has to be done unit by unit and slowly in order to preserve, obviously, strategy improvements. Yes. And in particular, what we'll do is identify an agent in the set of down, the guys who want to receive less, and this guy will give 1 unit from the Q that he has guaranteed to somebody in J. Yes. And the way of doing so, now let's assume that this, so let's take this definition. Yes, whenever the element is K, I cannot add 1 unit. So this could be plus, would be either 1 plus 1x or K, and minus would be x minus 1 or 0. Yes. So now the algorithm proceeds as follows. Yes, every agent now is asked whether he wants Qi less or more. We construct the partition, and if the 2 sets are non-empty, the up and down, now we go to stage B. If they are one of them is empty, or the 2, now the algorithm stops, and this is the Q. Yes, if they are not empty, now we go to stage B, and that's how we proceed with this input, the partition and the Q. And now this is the way we want to identify exactly, because not any Pareto improvement will it will do the job in terms of obviously strategy improvements, but not in terms of implementing exactly the rule that is given, the sequential alignment rule that is given. So now we look at this extreme situation, at this extreme profile. Yes, all the guys that want more, they are just, let's put them asking for K. The guys that are down, just the Q minus 1. And the guys that are staying okay, we give, it's like asking the Q. And we show that this is well defined. There exists at least 1 J that this is the case. And once we have this J, now we can define the R. So the pair is identified together. Now the individual that is in the set down that wants to receive less is identified now by this other extreme, where now here the guys in K, in U are put on K. Now those guys in down are put at 0. Yes. Sorry, my telephone is ringing. Sorry, I'm really sorry. And now we are giving to the guy who we identify here as going to go up. Now we are giving the guaranteed level of QJ, or even go above. And the guy who is in the down set, we are giving the guaranteed level of QR minus 1, or going further down. Yes. And now they make the corresponding adjustment of the sets. If this guy chooses this one, goes to the state NS. It chooses this one, goes to up, and symmetrically for the R guy. Yes, and that's it. Yes, we now update the Q according to these new references, and this is the output of the step. And again, if they are non-empty both, we go to the next step, and if they are empty, we stop, and that's it. I think it's a good moment to stop here. Sorry.
Thank you. Are you finished?
Yes. I think it's a good place. It's a good place to stop.
Okay.
Sorry,
so
he was calling me.
Sorry. We can. Thank you.
There were some.
Can you unshare your slides?
Excuse me?
Can you unshare? Yeah. Wow. Okay. Thank you.
Okay.
So, is there any question? So, you not that much.
Intention is not part of a formal definition.
There was a question by Bill. Bill Zwicker. I am wondering, Bill, can you go?
So I'm only following tentatively here, Jordi, but since there's this very delicate question of whether you're at Q, above it, or below it, I'm wondering whether there are any continuity conditions that hold for some of these mechanisms. In other words, we're talking about a discrete setting. So by continuity, I mean if you made the resolution greater by breaking each unit into a larger number of smaller units and scaling everybody's preferences proportionately, would you expect to get the final allocation that's somewhat similar?
Yes, I would say yes, because if you see the original definition of the in Barbara Jackson Nemen, they are, yes, they are. The point is that the difficulty of working in a continuous space is with the notion of obviously strategy proofness, is that you have to look at the first time that these two behavioral strategies differ. And I don't know, we were talking at the beginning with people who have been working intensively on an extensive form, and was suggesting that this might be a very difficult problem. So I don't know of any, for instance, Lee itself has an application for models which are usually continuous models, also does for a discrete. And we never started seriously with a continuous model, because you will have a question of how you define the first time of, and it defines a continuous, an extensive for game in a continuous way. And I don't know, Carlos Alós and co-authors have been working on this issue, and it's a very difficult problem. So, but my guess is now we are doing in a more refined grid of the units of integers. Yes. I wouldn't expect any discontinuity whatsoever, because the original rules are also continuous in the continuous setting.
Okay, we have another question by Peter. Can you say it, Peter?
Yes, right from the beginning of your talk, I was wondering about the relation between the number of agents and the number of items you are distributing. What you are saying also works if the number of items is actually smaller than the number of agents. So I was wondering whether these algorithms are designed for a large number of items or whether it's entirely arbitrary. If the number gets very large, evidently it relates to the previous question about the continuity.
Yeah, let me see. It works for any. The point is that now I'm describing a version. We had an earlier version, but it was much faster. This is much slower, because now every change is unit by unit. Anytime the reference just changed for one unit for some of the players. Yes. And we had an earlier version that we could go faster, but it's much more difficult to describe. But in any way, I don't have a clue whether this is going to be computational, NP, or whatever. I don't know. My guess is that it's going to grow fast in terms of the complexity of the algorithm when, for instance, the set of agents grows. Yes. We haven't explored computational issues, and in some sense, this new version of the paper, we are not even being less, much slower than we had. We could design the game in a more faster way, but now the problem is that we lose control of how this reference vector is changing. This one unit by one unit allows us to control very much this process of changing the reference vector. The individual rational rules are much simpler. When you don't have individual rational rules, now you have two different references, and this is a process of notating. The stage A is not only used to identify who wants to go up or down, but also to make the conversions of the two reference vectors, the one selected by the rule at when everybody says 0, or the one that everybody selected by the rule when everybody says k. The process of identifying, classifying the set of agents among the set that one's more or less or equal, it moves together with the two reference vectors until it converges to particular allotment, and then stage B works as in the individual rational case. Yes.
Would it be possible to have a continuous version which could be solved, for example, by linear programming methods, and then rounding the continuous solution to an integral approximation in some way?
Yeah, the reason we didn't go to the continuous version is the difficulty of even defining obviously strategy proofness, because obviously strategy proofness refers, you are comparing with alternative behavior at the earliest point of departure. And given two different behavioral strategies in an extensive form, this may not be well defined. So, and as far as I know, all the applications I have seen of this notion are done in a discrete setting. And my guess is that, I don't know, even the notion itself may be very difficult to describe, to define.
Thank you.
Thanks.
So if we don't have any other questions, no, I think we will close the session for this week. So yeah, another last question.
Who's that?
Anup Pramanik, characterizing, I don't know.
Oh, Anup. Right, Anup. Hello, Anup.
Anup? Anup? So characterizing sec, I don't know what it means. Well, if you can say it in the chat, maybe.
Oh, let's see. Anup. Is at the end or at the beginning?
At the end of the chat.
At the end.
Oh,
at the end.
Scroll down to the end of the
alignment rules with obvious. Ooh, set alignment rules. No, we haven't thought about that, but I don't know. I have never seen versions of the set alignment rules. I don't have a clue. I don't know.
Okay.
I don't know. I don't have a clue.
Good. So I think we can thank again the speakers.
Okay, thank you very much. Thanks.
So next week we'll have two other speakers. We have Leah Thierry from Princeton and Tetsuya Oshino from ITAM 2. And we will again be 1 hour later than usual. That is 10 a.m. New York, 4 p.m. Paris. And I don't know for all the Eastern European people, what time is it? But it's too late, I guess. So thank you, everybody. And we hope to see you next week. Thank you.
Bye-bye.
That's fine. You're still recording, Ula?
Yes, and I'm going to stop now.
Okay.
Bye-bye.
Bye-bye.